Welcome to another edition of Matrices. This is part 2 of the series. My name is Nate Nestler, and this is for Hyperactive Studios. Okay, so now if we have a look over here, now we were talking about earlier about doing matrices with multiplication and add, subtract, multiply, well, not divide, but distributive properties of them too. However, we said earlier that we would go into determinants and transpose. Right now, let's look at transpose because it's a simpler one. And essentially all we're doing here is we're just swapping our I and j, or shall I say our columns and rows with each other. So what would normally be, like 0, 0, 0, 1, 0, 2, 0, 3, etc., etc. We're swapping that around, so now it gets displayed in reverse. So basically, you can see the pattern here. So 2, 12, 14, 7. Now it gets written as 2, 12, 14, 7 going across on the row instead of down as a column. And so on and so forth throughout the rest of this too here. You'll notice some other patterns as we go along here too. So for instance, 4, 4, 5, 3 is now going across here. 4, 4, 5, 3. This is all there is to it. 8, 9, 6, 1 goes across now. 8, 9, 6, 1. And then, again here, 9, 3, 1, 5 is now going across 9, 3, 1, 5. Simple enough. So it's easily rewritten. From a programming standpoint, all you would have to do is literally switch your outer and inner variables for your loops for accessing your matrix, and as an array set or whatever, and bada bing, you will have it reorganized accordingly. So very simple from a programming standpoint in order to do a transpose of a matrix, and from a mathematical standpoint it's quite simple too. So this is really nice and really simple operation to do on any size matrix, matter of fact. Okay, so that pretty much covers transpose. So probably all wish they were all that easy. Here we're doing, next thing we need to look at is the determinant. So let's look at how to do a determinant of a particular algorithm, of a particular matrix, let's put it that way. And then that will lead us into inverting a matrix. So down here we're looking at the determinant of a matrix. Here I have determinant A here equals AD minus BC. Okay, well, that's how this works here. So if I have the matrix C here and I have A, B, C, D like this, and if I were to organize this as such, then I'll end up with that value for the determinant. And I can, well, more or less prove this if you like. Here I am going off script again. Seems like I do that way too much. Okay, so let's do a C here, and let's see if it will just go ahead and do the determinant for me right in here. So I know I calculated a determinant a second ago. I think it's just a DET around it. Oh no, it's this right here, written all the way out. Okay, it's DET in the other software, in Sage, I believe, if I'm not mistaken. It gets confusing after a while. Alright, Shift Enter, and bam, there it comes up, just like so, just like we have in the formula here. So yes, I proved it. That is how that works for that matrix C, for that matrix. Alright, so, and in here, if I want to invert a matrix, alright, so now I'm jumping right into inverting a matrix here. I'm going to take my determinant, what's 1 over the determinant times D over here times the matrix, where it's D, and then you have negative B, negative C, and then positive A. And when you multiply these across or whatever, you're going to get 1 over C, or shall I say C to the negative 1. Either way you want to write it, same thing. As you can see, I have it written as C to the negative 1 here, and then when it computed it, that's 1 over C, which is the same exact thing. So that's truth. That's accurate. Here I ran the determinant of A, and I got the value. So here's A initially, and then here's doing the inversion, inverting A. I'm sorry, not doing determinant of A, but doing inversion of A, inverting it, and I got this whole set of values here for that. So that's essentially what's going on. But you're probably saying, well, that's not a 2x2 matrix. That's true. And the way you would compute a larger matrix like this is more involved, I'm afraid. So It's not as straightforward as it is for 2x2. 2x2 matrices are spatial matrices where you can do certain operations on them to make life easier. Unfortunately, that's not going to be the case on a larger matrix here. So let's have a look at a larger matrix and see how we go about doing a determinant on that. So if I were to do the determinant of E here, I would have this kind of calculation going on here. And you're probably wondering, well, wait a minute, where did that come from? How did that happen? Well, it's not too bad. I did an expanded matrix form here in F so that you could see the actual calculations. Otherwise, you won't see it, but you literally would draw these other values here because, okay, basically we have E right here if we just cut it off right here. And then if we were to have these values basically like sitting outside of the matrix just so you can see, it's just repeats of these other ones here so you can just see how the algorithm works for doing the calculation. So it's real simple. We do E11 for being the first element in the matrix, right? Row 1, column 1, times E2, column 2, row and column 2, and then E row 3, row and column 3 here set up. So you can multiply those together. You see you get this nice diagonal going across here. Now we do the next one, it's another set of diagonals, and we add it to the next set of diagonals, and check it out. Yep, E12 times E23 times E31. So check that out. Straightforward and easy to follow. And then, so you can see why we had to expand this form, because at this point we've ran out of space to continue doing this, diagonal method here for understanding how to go about it mathematically. So by adding the same, copying this matrix here, and then this chunk of matrix right here for this block, was selecting the whole thing, sorry. From here on down and then over in this little block here, going from E11 all the way down to E32. If we're copying that back over on this side, then we can do the calculation. So continuing on, doing another diagonal across here. So E13 times E21 times E32. So, we're doing element E13 times E21 times E32, just like I said. Alright? And we're adding those together. Now we're going to go across the other way. So, we're going to cross it this way. When we cross it back the opposite way, we do subtraction. So, here we go. We're going to cross it back the other way now. E13 times E22 times E31. Alright? And we have put a negative in front of that. If you want, you could put parentheses around this and then have a -1 over here, or just a negative, whatever, it doesn't matter. It's going to give you the exact same value either way. Okay, and then we're going to do it again this way here. So crossing it the other way now, E11, E23, E32, this way, like that. And what we get, negative times this, because again we're going the opposite way. So E11 times E23 times E32. Okay, and then again subtracted from the next row here. So we're going to do another diagonal here. So again, because we're going this direction here versus this direction, it's going to be a negative. So E12, E21, and E33 need to be multiplied together, and they are, and with the negative there. All right, so all this together gives you the computation of the determinant of that form, and then that is literally how you're going to solve a 3x3 or a 4x4, same kind of method. You just set up these diagonal approach here and work it out that way, and you'll get the result for any size matrix. So you can see there's a difference between doing a 2x2 versus a 3x3 or a 4x4 or something like that. And that's how you can solve a determinant on there. Let's see if I can't just prove that real quickly to you. Copy that, because you can copy and paste. That's really cool. I love that aspect of this. Alright, so let's go ahead and throw that in there real quick. Paste. And then this was E, I believe. Yep. Okay. And semicolon and shift enter. And bang, there it is. And, well, it's the same thing, but it's written up differently. But you get the idea. But it's the same thing. It's just written up in a different form of it. But it's easiest to visualize it like this here. That's the easiest way, I think. visualize it. And basically that will give you the determinant. And so we looked at how to do an inverse, a determinant, and also how to do the transpose of a matrix. Alright, one other thing we need to look at here, and this is a rule set. And this is for doing commutative properties and things of this way nature. So this is what you're allowed to do. So you can do A plus B, if you have two matrices here, right, of the same size, A plus B equals B plus A. This will work out. You can multiply, you can add them together in any order, and it's going to work. You can also add, plus A with the parentheses around B and C for, three different matrices here. Would be the same thing as doing A plus B with the parentheses around it plus C. You get the exact same result. Distributive properties here for multiplication. So you could sit there and say A times BC or AB times C. Either way, we're still keeping the order the same, so this is allowed to be done. We can also do distributive this way, where we have two additive properties here. So A times B plus C is going to be the same thing as AB plus AC for matrices. And then over here, if we do in parentheses B plus C and then times A, that would be the same thing as saying BA plus CA. Now that's important because it does come after it. The order of the multiplication is important. You cannot switch around AB plus AC. That would not work. That's not the same. Okay, AB minus C would be the same thing as AB minus AC, and that works, and that's doable. You can also do B minus C times A in parentheses, and you'd end up with BA minus CA. That's allowed also. Here we have a single value being distributed across our, capital letters here are matrices. The little variable here could be a number, if you will, to be distributed across the matrices here. So this isn't a matrix. This is a value, like a constant or a any kind of numerical value or something like that, or a variable for that matter. It doesn't matter. You can have the same thing either way. So A is going to get distributed across B and C. So it'd be the same thing as saying A times B plus A times C, little a here being this value. That would be the same thing. Also, A times B minus C, of course, is going to work just fine too. So AB minus AC is also going to be compatible. And then we have in parentheses here A plus B here for two values possibly being added together, and then being distributed across C, which would be the same thing as doing A distributed across C plus B distributed across C for the matrix, and then having them added together. And that's the same thing also. A minus B times C here for distributive, and will give us AC minus BC here for distributive, going across those values in those matrices. The value A here multiplied times the value of B distributed across C is the same thing as saying A times B then distributed across C. So that works. Also, A, B, C here we have A distributed times across the multiplication of matrix B times C. Would be the same thing as distributing A across B first and then multiplying it times C, which would be the same thing as distributing across same thing as having B multiplied times A distributed across C first. That works also. Doesn't matter, you're going to get the same values either way, however you do it for any of those. And then here I'm just showing that the inverse of a matrix times itself will give you the identity matrix. And likewise, you can switch this around either way. You can have your matrix then times the inverse of its matrix, and you'll still get the identity matrix. So you can literally multiply that either way, and you'll still end up with the identity matrix just fine. And you're not going to have a problem for multiplication. And the reason that's the case is because either way you multiply these across, it is the same matrix, so therefore it has the same layout for its rows and columns. So that's why it works. Okay. And then we have here, I just showed earlier, I talked about the determinant of A and what the equation is for that. So that lays out what rule sets you can have for the matrices, and how to do the determinant, how to do the transpose, how to do an inverse of a matrix, how to do it on a larger, how to do the determinant on a larger one or smaller matrix, a 2 by 2 versus a 3 by 3. We could have done even a larger one, but didn't want to. Make it easier if we just stick with the smaller ones because it's fewer mathematical operations to cover. So that's essentially how it works for doing these matrices, and I hope that is pretty clear. Alright, and this is also another example of how to use a bit more of our wonderful maxima here, as it does all kinds of wonderful things. And here's the determinant right here. So if I had selected a matrix, like for instance, okay, so earlier I typed it in. I didn't have to type it in though. I could have gone in here. Say I wanted to solve like the determinant of Z, for instance, here. So let me add a new. Let me add a new one here. I think I hit the wrong thing. I'm kind of nervous about leaving that there. Okay, there we go. Alrighty. So say I have Z in here, right? And I want to take the determinant of that. No problem. Take my Z here, and I'll just come up here to my algebra, and I'll say determinant. Bam, there it is, and it did the determinant of it. So that is a way which you can use these menus up here in order to do these. You do not have to memorize every little special command here for doing the mathematics on it. As long as you know what you're doing mathematically and you understand how the mathematics works and everything, then you can just easily find the magical script syntax, for running the calculation or the formula aspect of it. And again, the wonderful, beautiful thing about this program is that it sure does display things in such a pretty form. So here I typed it in like this, and then it displayed it properly as you would actually write it on paper. Beautiful. Very nice. Makes it very nice for presentations, and also makes it really easy for you to follow and see what you're doing and not get so confused. So that way if you realize, oh, I put that parentheses in the wrong place, or I did something in the wrong place here, I get it in a more human readable form where I can really easily see what I've done wrong or done right. You know what I mean? Because the formula should lay out like you would expect it to for the most part. And this program does a very wonderful job of that. And this is a free open source method for doing these mathematics, and so it's extremely cost effective and will hopefully help you in your research. And don't forget, you can also graphically map algorithms here in this program here, so you can do 3D graphing and stuff for Calculus 3 if you need to, and that's very nice indeed. Alright, so with that, let's go ahead and look at how we can use our matrices in 3D graphics programming here next, and how we can deal with rotation matrices X, Y, or Z, and do rotation order based on multiplication of these matrices. How to do transforms, basically translate for how to actually move it. Now, transform would be rotation, translate, and scale. You know what I mean? So we're going to be doing our transform matrices, where we combine these multiple matrices into one, and not do these mathematical operations on a per rotation basis, which would slow down our calculation significantly. So for our frame rate, it would multiply our computations immensely, let's put it that way. The more rotations and movements and scales we do, the bigger impact it is on performance, unless we multiply our matrices together beforehand, before we actually modify our model, our 3D model. So we're going to look at that next. Alright, so that covers our determinants and our transposes and our inverse matrices, and how to get a identity matrix, and also the rules of matrices for basic setup here. Okay, now let's look at the rotation, transform matrix, and the translate and the scale transforms, and how those matrices work, and how we can apply those to different vertices within inside of a 3D model. Okay, so with that said, what I did was I created a couple matrices, more than a couple, about 5 to be accurate, and I just did a transform matrix here. So first off, let's see what the layout is for a translate matrix. So here we have our straight ones all the way down, just like we would for our identity matrix. Remember, identity matrix is straight ones all the way around here and zeros everywhere else. TX for my translate and X, TY for translate and Y, TZ for translate in the Z axis. Alright, over here for scale, works a lot like translate, but it's a little different. It's going to have zeros here where the translate would be, and then we're going to give different values here along our diagonal here. And so SX here is going to be a different value. So this means you can have non-uniform transforms for your scale. Okay, it sounds like a fancy word, but basically what this means is we can scale a different size in X versus a different size in Y and a different size in Z. So that's what non-uniform transforms means, or translations, or scale, non-uniform scalars. Okay, so with that said and done, basically we can have different values here. We could also have the same value and uniformly scale our matrix, or our model, our 3D model. And basically what we do is say we want to scale it 5 times, right? So it'd be 5 here, 5 here, 5 here. You know, that'd be different than a non-uniform scale. Maybe I want 3, 2, 5 here, like that, you know. So then, you know, on scale along the z-axis, it's going to get scaled more than the other ones here. And of course, x more than y. But that's how the scale one works. Okay, now we get into a little fancier stuff here. Yeah, I'm just going to delete this one real quick because I don't like that. Okay. Well, this gets into our Euler rotations. So if we look at our Euler rotations from Wikipedia, we'll see that we have our rotation matrices like this. They're doing rotation about y here first. So basically you see a noticeable pattern here, right? So if we're going to rotate about y, that's the one we're not going to affect. We're going to affect x and z because we're rotating about y. Now they got some wonderful explanations of it here, and I do want to make use of this. So here's a nice little animation here that's showing off these different rotations as they occur here. And this gets into rotation order. See how it's rotated here first and then that direction next? That gets into your rotation orders. So that really matters a lot. And we can see this. So say we want to rotate about the z-axis, right? And it's going straight up and down. That means we're going to rotate about y and x here. And by manipulating y and x, we get an object to rotate about z, because the z-axis is not being manipulated, just the x and y is. So that's how that works, and so that's why it's so cool, and this is a very good write-up, and it explains things quite well. Well, math is a little difficult to understand, I guess, on some of this, but if you're new to this, but this is very well graphically drawn out and done. It's very nice. It's very well done. Beautifully done, indeed. Alright, so going back here real quick. Alright, so we have our rotations about y, and here's the ones for x, and here's the one for z, because again, we're rotating about z, so that's the one we're not manipulating here. We're not manipulating that one there. So it's staying the same here. Same thing here goes for the x. We're not going to manipulate x, so therefore we're manipulating everything else around it. And so that's kind of like basically showing you how to go about it. Since we can have rotations here separately from one another, then it matters that, you know, how this lays out, basically. Okay, so this is our x Euler rotation matrix, and this will allow us to rotate around x, of course, and because we have our 1 here, and our algorithm's laid out properly here. Here's the one for y. So here we are rotating about the y-axis, and then here we're rotating about the z-axis here for our Eulers. Alright, so I've kind of already explained all this, so in order to do a demonstration here, though, I wanted to show what would happen if you were, what happens underneath the hood with these different 3D languages and things of that nature as what's going on. And you need to understand this in order to manipulate things into doing crazier mathematics, in order to make the programs do what you want and bend to your will, more or less. Otherwise, you're going to be stuck with doing more basic graphics, and your stuff's not going to look that good. So in order to get to the more advanced graphics and to do better and more complicated tasks, you're going to have to know this mathematics and have a full understanding of it so that you can actually implement it in the programming. Much less if you're ever going to derive anything on your own and develop something that's actually groundbreaking or useful. So pretty much you have to know this, alright? So here we have our translate along x, translate along y, and translate around z. So here I am moving in 5 units in x, 4 units in y straight up, and then in the depth axis here 3 units into the screen, if you will. Okay, so over here is my scale matrix, and I decided to do it real quick. So I did a 3 here, so I'm scaling my x 3 times, I'm scaling my y twice, and I'm scaling my z 5 times larger. So that does the scale matrix. Here's my rotation about x. So I decided to do it 90 degrees, or pi over 2. Same thing. If you think about 2 pi is a full 360 degrees, pi is 180, and then pi over 2 is going to be 90 degrees. Okay, so here I am doing it about the x-axis, so here I am doing cosine of 90 basically, and sine, negative sine of 90, and so on and so forth here. Sine over sine 90, and then cosine 90 here, and so on and so forth. Same thing goes for the over here. I decided to do 45 degrees, right? Because half of 90 is 45. So if I divide pi by 4, I get 45 degrees. And so I'm putting in 45 degree manipulations about the x and z axis in order to rotate about y, and make it rotate basically 45 degrees on y. This is going to rotate 90 degrees about x, and then this one's going to rotate 180 degrees about z axis. Okay, so how do we do this? Well, order of operations really matter. Remember how we have to multiply things in a certain order? Well, that hasn't changed. We have to multiply it in a certain order in order to get the proper result. So I'm going to multiply backwards from the order in which I'm going to do something. So say I want to translate first, then rotate in x, then rotate in y, then rotate in z, and then scale it. I have to do it in reverse order. So I'm going to multiply it first by scale, then rotate z, then rotate y, then rotate x, and then translate matrix. I have to multiply it in that order. You might be thinking, well, why not just apply this directly to the entire model one by one? Well, if I did that, and I have 5 of these manipulations here for our matrices, I have to multiply this matrix across all the points in the model. And say I have like 30,000 points in my model, right? Well, I just did this. Well, let's keep it easy. Let's say we have 10,000 points, all right, in the model. Well, essentially that just meant that I just manipulated the thing. I just did 50,000 computations, because I just had to multiply this matrix through. Well, yeah, actually it's more than 50,000 computations, because it's x, y, and z axis here for each one. So take that, and it's like 150 computations, or 200 computations, 200,000 computations if you get down to that 1 there too, because you have this 1 here for the mathematics to work out properly for you. Okay, so that really matters. So if we multiply these through first, we get our transform matrix that is composed of all of the above. So it'll be composed of our translations, our rotation on x, rotation on y, rotation on z, and the scaling. And we get one super matrix here that comes our transform matrix. And that is one of the nice things about this program, is that it will actually just compute it out and show you what it will be in, not in numeric form, but in a finalized form here as far as the values go. You can see why we needed a 4x4. You notice here that we actually take up that 4x4 space there. So that's really important. If you don't have the 4x4, it's not going to work. So that really matters a lot. So be aware of that, because it really does matter a whole lot. It's important. Okay, and so in order to be have a little more interest in it, so here's our point in space. It's inside of our model. I'm just doing this on one vertex here just to show how it works. All right, and then I'm going to come in here, and I'm multiplying my vertex matrix, which is a 4x1, times my transform matrix of a 4x4, and I get my resultant here. And so this is the final result for each part of that value here for our transform, for our vertex here. Okay, and then tried to do a number evaluation on it, wouldn't work, so then I ended up putting in 3.14 for pi in each one of my rotations in order to get the compute all the way, because it wouldn't compute pi with me putting in numer by itself for whatever reason. It just wouldn't do it. So I had it recompute accordingly, and then I did the calculation here, and then we get it all in numeric form. And then when I do the multiplication through here, then I get my actual numeric form for my transformed point. And so this is a new position for this point after it's been translated, rotated in x, rotated in y, rotated in z, and scaled. And this is its final position here. And so I don't have to sit there and do each one of these operations and move this point 5 times. I simply just move this point 1 time. through this operation. And so here's the original position of the point, and then here's the modified position after the transform matrix for the translate rotate X, rotate Y, rotate Z, and scale. Alright, and that's how it works. And it's really important. You'll find this being used for all kinds of things, including projection view for manipulating matrix in order to make it the points actually deform so that it looks like you're getting camera lens distortion and all this kind of stuff. And so in order to get to draw properly on the screen. So all these kind of things really makes a major difference on it and how it's being manipulated by the camera angle and such. Very cool. So hopefully this was interesting to you and useful, and you learned a lot. Not to mention you'll be using this like crazy, including in some of the following videos inside here, some of the shading development, and when we're also doing OpenGL programming and such, we're going to be using this on a regular basis, and you got to get used to it. We'll probably be using it in OpenCL and CUDA maybe even too. So for those reasons, you'll see this over and over and over again as we run into it, and we'll constantly be using it. Just to explain the actual pipeline for the shading pipeline, you have to have an understanding of how this works, just to even understand how we're actually even drawing stuff on the screen, and the process of how to get the model from, in the mathematics to the screen, and what's going on underneath this hood, and how we're going to take that mathematics in and apply that to our models and to our shading to actually manipulate the models and the shading to get the results that we want. So this is just absolutely vital. You have to understand it. If it didn't make sense to you completely first time, go back and watch the video several times. You may need to. It's extremely important. But with this, that covers matrices. This is part 2, and it's the end of part 2. And my name is Nate Nestler, and this is for Hyperactive Studios. Thank you very much.